Hi folks, welcome to lesson 1.5, modeling solving problems with polynomial functions. Now that we've learned all about polynomial functions, we're going to be doing some problem solving with them. See where the application of polynomial functions really is. So before we do that, a couple of things that I need you to do. I need you to go into your work text on page 57 and try the check your understanding and get started warm up. So do that first. And then once you've done that, you can pause the video right now, go ahead and try that, come back here, and then we'll continue on from there. So make sure you do that first and then continue on with this video. Now that you've got a bit of a warm-up, let's review some key concepts you learned way back in grade 10. So one of the things you learned back in grade 10 was the surface area and volume of 3D shapes. So we know that if you have a rectangular prism, this is the length, the width, and the height. We know that the volume of this shape is length times width times height. And we also know that the surface area of this shape is, there are 6 surfaces, so 2 times the length times width plus 2 times the width times height plus 2 times the length times height. You also learned about cylinders. We know this is the radius of a cylinder, that's the height. So volume of a cylinder is pi r squared h, and the surface area of a cylinder is 2 pi r squared plus 2 pi r h. That's a couple of review items that you're going to need to know for this lesson. Our goal in this lesson is to look at problem-solving problems and try and model them using polynomial functions, and then use the graph of a polynomial function to try and find some maximum or minimum values. So here's our first example. We have a piece of sheet metal that is 25 centimeters long by 18 centimeters wide. It's going to be used to make a box. We're going to cut the corners up and we're going to make a box with no lid. So equal squares of side length x centimeters are cut from the corner, so that way they're folded into a box. So what we're going to be doing is I'm going to start off by labeling this diagram. I have a box with length of 25 centimeters and I have a width of 18 centimeters. And this box I'm going to take and I'm going to cut it up. I'm going to cut corners from here and I'm going to cut corners from here. So if you have a piece of paper at home right now, you can actually try this. Take any standard piece of paper, if it's rectangular in shape, and cut the corners. And once you cut the corners and you fold it up, you basically are going to get this side to join up with this side. I'll show you. If you get this corner here, once you cut it up, and you get it to join with this corner, and if you take this corner, match it up with this corner, and this corner, match it up with that corner, this and this, and you tape those up, what you're going to end up with is a box, and your box is going to look something like this. And I'll draw the front view of the box. Right, and you're going to get a box that looks like this, the folded up version. Now let's look at the dimensions of this box. Because you have cut off corners of side length x and x, x and x, x and x, x and x, what's going to be left is at the bottom your new length is going to become this part right here. So this part here is going to be the 25 centimeters you had before, subtract the 2x. So the new length becomes 25 minus 2x. And similarly, if you look at the new width from here to here, once you cut those corners off, your width is going to become 18 minus 2x. So that's the new length, that's the new width. One of the other aspects we get when we fold it up, we're now going to have a height or a depth, and that depth over here is going to be of x centimeters, because that's the part that's folded in, and that's going to have a length of x. So that's the 3D shape that we get. We want to use a polynomial function to first of all represent the volume v of that box in terms of x. So what I'm asking for is, what would be the volume of that rectangular box? Well, we know that the volume formula for rectangular prism is length times width times height. Our length, width, and height are those values. So as a result, the volume as a function of x of our polynomial is going to have the expression x times 25 minus 2x times 18 minus 2x. That's going to be the polynomial. Now we're going to have some restrictions here, and the restrictions are going to come from the way this function is set up. We know that in physical parameters we cannot have a side length that's negative, so as a result we know that from here this x value is going to have to be a number bigger than 0. We also know that this expression over here has to be bigger than 0, so 25 minus 2x has got to be bigger than 0, which means 25's got to be bigger than 2x, which means x is going to have to be less than 12.5. Alright? From this expression over here we also get a restriction. We know that that aspect has got to be bigger than 0. We cannot have a negative side. So from there, if I solve that inequality, I get 18 is bigger than 2x, which means x is less than 9. These numbers are going to help us set our domain. Okay, we're going to have some sort of a domain restriction overall. If x is a number bigger than 12.5 and x is a number less than 12.5, x is a number less than 9, and x is a number bigger than 0, then what I get here is that x is going to have to be a number that's bigger than 0 and less than 9. That's sort of the overall domain that I get. Good? Alright, next up. I've asked you what the domain is. I just looked up over here and I figured out, based on the parameters given to me, the domain of this function is going to end up being x has to be a number bigger than 0 and x has to be a number less than 9. If you didn't quite catch that, you may want to pause the video, go back and re-look at the explanation I gave you for that. And that's what the domain we're going to be working with. Now what we're going to do, now we're going to go ahead and take the polynomial function and we're going to create a graph of that polynomial function on your graphing calculator. I will give you a moment to go ahead and try that. Take this expression, plug it into your graphing calculator and see what kind of graph you come up with. I will do the same. We will compare our answers in just a moment. Okay, so what I've got here is I've got the graphing calculator. I'm going to show you how to plug this in. You've hopefully already done that. I'm going to go here and plug in the polynomial y equals, I have x times 25 minus 2x, 25 minus 2x. And then I have the third factor, which is 18 minus 2x. And I've sort of created that graph, but you'll notice really you don't see much on the graph in there. Part of the reason is because we haven't set the proper domain and the range. So I'm going to go ahead and adjust that. I'm going to go under window settings over here, the window button. I know that my domain of that function is going to be between 0 and 9. So I'm going to set the window settings that's going to show me that domain. I'll change these up to -1 all the way until 10, because then I'm going to see a bit of the window on each side of the domain. Now I'm looking for a function that's going to have a really big y value. Think about what kind of numbers we could plug in here. You could have a length, width, and a height of, say, 5, 10, 15, and then that number will be a really big number, at least in the thousands. So I have to adjust the y scale accordingly. So I'm going to leave it like that. I'm actually going to make it 0 for the minimum, make it 1,000 here for the maximum. And that number I got just by looking at the type of problem I have and what kind of context I'm working with. I'm going to create that graph. And that's the graph I'm going to get. Now sometimes it's really hard to just guess that number and figure out what kind of shape my function is going to be. So one of the other features we can use is we can look at the zoom button here. And if I go zoom and press zoom fit, which is one of the options at the bottom here, option 0, what the graph will do is it'll create a graph that sort of fits your window settings. And you get a chance to look at the full graph in terms of where we're interested. We are not interested in the graph where it's x less than 0. We're not interested in the graph where it's more than x bigger than 9. So I can also adjust the settings back here, and I've already got that. Now what do we do with this? I want to use this graph to try and figure out what is the maximum volume of this box. This polynomial function right now represents the volume of your graph. As you change the length and the width, the polynomial function is going to have a different volume attached to it. This graph here is representing x values represents what size square you're going to cut off, and the y values are representing what your total volume is going to be based on that adjustment. You'll notice that if you cut off a bigger square, then your volume is going to change accordingly. If you cut too big a square off, then your volume is going to be really, really low. But we're interested in finding the maximum point over there. So to do that, we're going to use the following steps. We're going to go second, trace. We want to find the maximum, so option 4. It's going to give you a left bound and a right bound. Now you can notice I have a really hard time seeing the cursor on there. So one of the adjustments I'm going to make here is I'm going to go back into window settings, and the Y max here is 693. I'm going to change it back to 1000. Now I have space up at the top of that graph, so when the calculator spits out its answers or its values, I still have enough space to see my graph. Zoom fit is a good feature to give you a general range of where your graph's going to be, but then you still have to adjust that accordingly so you see a nice clear graph on your window. So again, second, trace, maximum. To find the maximum, it's going to ask you for the left bound, which means you got to scroll over to the left of that graph, or the maximum of that graph, which is up there. Press enter. Then it's going to ask you for the right bound, so scroll to the right using the arrow key to the right of that maximum. Press the enter key, and then press enter for the third time, and it's going to tell you that you have a point 3.44 and y value of 693.14132. That's your local maximum on that graph within the domain that we are working with. So let me make a quick note of this. I will do a quick screenshot. So I've done a quick screenshot for you here, and this is what we end up with. So this point here, this point is representing 3.44, 693.14132. We just want to make sure we make sense of what this graph is representing. If you look at the polynomial function we're working with, the y value is the function volume of x, and the expression is a product of the 3 dimensions. The x value that we're plugging into the graph, that's the size of the square we're cutting off. So what this graph is representing is, depending on what side length of square we cut off, what is our overall volume going to be. If we cut off something, let's say size x box of size 1 length, our volume is going to be up here. If we cut off a square of size length 2, we're going to have a higher volume, and so on and so forth, until a point where we get the maximum volume. And if we cut off a square that's too big, say size 8, then we're going to take too much off that box, and our overall volume is going to be less than the maximum. So that's the whole idea here. We're trying to find a way to optimize and maximize our overall volume. And we find that when we take off a square length of box, square length of 3.44 centimeters, that's what we're cutting off here, centimeters, then that's the point where we're going to have the maximum amount of volume. So as a result, we can say the maximum volume occurs when we take off a size length of 3.44 centimeters, and that volume ends up being 693 centimeter cube, because it's volume. Which is the next part. What size square should we be cutting off? We get that maximum volume when we take off 3.44 centimeters from the corners. So we need to cut out a size or square. So cut out square of size 3.44 centimeters by 3.44 centimeters. Okay, that's the size length of square you're going to have to cut off. So that's what the measurements need to be of that square here, so that we get the maximum volume of that box. And what will be the final dimensions of this box? Now it's just a matter of me going back and plugging in the value of x into the length, the width, and the height, and figuring out what the dimensions of this box are going to be. So as a result, I know that the length of this box is 25 minus 2x, which is 25 minus 2 times. I'm taking off 3.4 centimeters out of there. I'm rounding to the nearest tenth, so that's why I'll keep 1 decimal place, which will end up giving me 18.2 centimeters. The width is 18 minus 2x, 18 minus 2 times 3.4, which works out to 11.2 centimeters. And lastly, the height was simply x, which works out to 3.4 centimeters. So when we write the answer, we're asked for what are the dimensions of the box. So we say that the dimensions of our box are going to be 18.2 centimeters by 11.2 centimeters by 3.4 centimeters. Those are the dimensions of our box. So this is one example which shows you the practicality of polynomial functions. They can be used to model maximization and minimization problems. Here's a really neat application problem you've seen over here in real life where polynomials come into play. Example number 2, I'll let you try. We will discuss the answer to that in class tomorrow. I want to move on to example number 3 now. Let's take a look at our next problem. The one that we did earlier, if you notice, ended up becoming a cubic function. It was x to the power of 3. This example here is going to represent a polynomial function that's going to be a quartic, power 4. So let's go ahead and set this example up. Example says, Leo and 3 friends each have birthdays on December 13th. Sandy is 3 years younger than Leo. Leo is 4 years younger than Vince. Hunter is 1 year older than Leo. And on December 13, 2010, the product of their ages was 5, 4, 6, 5, 8 greater than the sum of their ages. How old was Leo and each friend on that day? So lots of wording over here. We need to sort of decompose that and try and figure out what exactly is going on. When you're working with word problems, the first thing I ask myself is, what am I missing? For that, I look at the last sentence. The last sentence asking me how old was Leo and each friend on that day. So I'm going to start my problem by analyzing that sentence. I'm going to first answer that question. How old was Leo on that day? I don't know. So let me give it a variable x. So let's say, let Leo's age be x. If Leo is x years old, then we know that Sandy is 3 years younger than Leo. So we know that Sandy's age will be x minus 3. She is 3 years younger than Leo. We also know that Leo is 4 years younger than Vince, which means Vince is 4 years older than Leo. So we can say Vince's age is x plus 4. And then lastly, we know Hunter is 1 year older than Leo. So we say Hunter's age is x plus 1. So this is all the information that's given to me in the first couple of sentences. Now the next sentence that I haven't used yet, that's going to give me my polynomial function. I am told that on December 13, 2010, the product of their ages was this amount greater than the sum of their ages. So I need two things. I first need the product of their ages. I need sum of ages. And then I need to relate those two expressions using this statement right here. So let me first figure out what the product is. The product of their ages is going to be a product of all these numbers. So that's x times x minus 3 times x plus 4 times x plus 1. The sum of all their ages is going to be the sum, x plus x minus 3 plus x plus 4 plus x plus 1, which I can actually simplify to, let's see here, x, 4x minus 3 plus 4 plus 1, so 4x plus 2. That's what I get. Now, what's the relationship? We know that the product of their ages is that amount greater than the sum. So what that statement is saying is, if I just make mental notes, the product is equal to this much amount greater than the sum. So sum plus 5, 4, 6, 5, 8. Now I can replace the words product and sum with their actual algebraic expressions or polynomial functions. So the expression I'm going to get is the following. X times x minus 3 times x plus 4 times x plus 1 is equal to the sum, which is 4x plus 2 plus 5, 4, 6, 5, 8. And this I can sort of collect like terms again, and I'll get this expression. X times x minus 3, x plus 4, equal 4x plus 5, 4, 6, 6, 0. This is going to be the polynomial function that I'm working with for this example. Once we have the equation figured out, all we have to do now is graph that function and solve for x. We're basically looking for the roots. So we're going to use a graphing calculator again to graph this function, and when we find the value of x, we're going to find Leo's age. So in this particular case, we're not looking for a maximum or a minimum. We want to figure out what value of x will satisfy that equation. It will make the left hand side equal the right hand side. One of the ways we can graph this is we can graph the left hand side and the right hand side separately as two separate functions and see where they intersect. Or if we want to make our life a little bit easier, what we can do is we can bring everything over to one side, graph that function, and look for the zeros, look for the roots. And whatever that root is, that's going to be the x value that we're looking for. So let's go ahead and try this, see what we come up with. Our function here is x times x minus 3 times x plus 4 times x plus 1 equals 4x plus 5, 4, 6, 6, 0. If I bring everything over to one side, I'm going to get x times x minus 3. I don't need to open up the brackets. I could if I wanted to, but that just makes more room for mistakes. Because we're going to be just graphing it using graphing calculator anyways, there's no need to really open the brackets up and collect like terms. We can just leave it like that. Once we've got an equation equal to 0, to solve this problem, graph the above function, and look for zeros. Our goal is to solve for x, right? That's what we're trying to look for. What is Leo's age x? So to solve for x, this is no different than solving any other equations you've done in the past. Solving quadratic was really easy. We just factor it. Solving cubic, we could factor it. If we open this up, we can solve algebraically as well. It will just be a quartic function, but we're going to do it using graphing technology. Now it's a matter of graphing this function, looking for the zero. So I'll let you go ahead and plug this into your calculator, look for the zero, and we'll compare answers. So once I've plugged that equation into the graphing calculator, what I need to do now is I need to find where this graph's going to hit 0. So when I look at the window settings, because I'm looking for the 0, I really don't need to make too many adjustments. The only values I will have to adjust are the x values. I want to figure out what my x values are going to be. X represents the age of a person. I know that the age is not going to be a negative number. So as a result, what I'm going to do is I'm going to go ahead and change the x minimum to 0. I'll make the x minimum a little bit big number. The age of the person can go anywhere from say 0 to 60, 70. I'll be safe, make it 50. And the x scale factor, that just tells you how far apart the subdivisions are going to be. I'll make that x scale factor of 10. So the y minimum and the y maximum, I'll leave it the way it is because we don't need to worry about that. We're looking for the 0. So our graph is going to hit y equals 0 at some point in time. Let's create this graph and see what we get. When you create that graph, you're going to get this line. This is a much bigger graph. We're just seeing the part where it touches the x-axis. That's the part we're interested in. That's the point we are interested in. Now it's just a matter of us finding out what that 0 is. What is that point? So to do that, we're going to follow the following steps. We're going to go second, trace, 0, option number 2. It's going to ask us for the left bound, so I need to be on the left side of that point. Now notice I had set my x scale at 10, which means each of these subdivisions is a 10. This is 10, this is 20. I'm going to scroll left until I see a left bound. Either I see a star passing by here, and if I don't see that, then I'll just have to make sure I get to a left bound that's to the left of that line. I know x value of 9.57 is going to be on the left of that line. I'll press enter. I'll see an arrow here. I need to go to the right of that line, and I'll go to a number closer to 20. Press enter. I'm to the right of that line. I know that my line, my graph, is between those two arrows. Now I can press enter for the third time, and what the graph's going to do is going to tell you that you have a 0 at x equals 15. That's where the 0 is. So we now have a possible solution for our graph. So as a result, we get x equals 15 as our solution. So what does this mean? This means that we can now answer our question. X represented Leo's age, so as a result, Leo's age is 15 years. We know that Sandy, as a result, x minus 3, so Sandy is going to be 12 years old. Vince, x plus 4, Vince is 19 years old. And lastly, Hunter is x plus 1. Yeah, so Hunter is going to be 16 years old. And there we have it. We have used polynomial functions to answer that word problem and find the age of all the people in that example. The other two examples that I haven't done are very similar to the ones that we've just covered. So now you have example number 4, same idea, different numbers, as well as the example that we had skipped earlier, which was example number 2, same idea, different numbers, just for you to give it a try. So what I will do is I'll give you the answers right now to example number 2. You go ahead and try them and see if your answers match up. When you try example number 2, the maximum volume is going to end up as 1512 centimeter cube, and the size of square that we're going to be cutting out will be 4.5 centimeters. And similarly, when you try the last example, it's exactly the same with different numbers. I just want you to get a practice on all the different concepts we've learned so far. In this case, it's asking us how old was Clara, so I'll give you Clara's age and you can figure out the other friends. Clara will end up equaling 17 years. So go ahead, give those examples a try, and if you don't get them, we can talk about these in class tomorrow. Thank you for watching the video. Good luck with your homework.